All right, I think we're live, but let's double check. Twitch, that looks promising. Sweet. All right, awesome. Hello, everyone. Welcome to today's office hours. We are rapidly approaching the deadline for cryptography, which, let's see here, when's that due? Well, we saw when it's due. It's due in 12 hours very soon. How far are we through this course? We're getting to the end. Well, close. This is 6 modules. The 6 modules almost done. I think there's a total of 9 modules. So yeah, we're rapidly making progress through this semester. And let's jump into it. Let's see, we got some number of people here in the chat, so that's always good to see. And let's talk about cryptography. I'm gonna have this be a little more open-ended, assuming there is interest in that in the chat room. Is there any, I guess, specific questions that people have regarding cryptography? Things that aren't making sense, stuff that you want to explore further, etc. Or is everything just making sense? I should have seen if there was even interest in an office hours for today. No one has any questions? We are not seeing any questions at all. Nothing. All right, here's what we're gonna YOLO do. We're gonna look at the Discord. I'm looking at it on my phone. I don't know if that's in the camera shot or not. And what I'm gonna do is I'm gonna click on cryptography and see what people are talking about. You know, I see a lot of things talking about level 6. What's the link for the Discord? If you go to pwn.college, up at the top, there's this chat button, and I think that takes you to discord.gg/pwn.college, I think. No, let's see here. Copy link. Yeah, discord.gg/pwn.college. All right, so I see on the Discord, just like scrolling through a whole bunch of messages, I see a whole bunch of people talking about level 6, which is actually surprising. I didn't realize, I don't remember at least level 6 in the past being a pain point, but let's go ahead and think about this. I'm trying to see why there is a lot of frustration surrounding level 6. Maybe there's some sort of conceptual misunderstanding, or is there something annoying about the challenge itself? That's what I'm wondering about. Well, let's actually just jump into level 6 and see what the heck this level's talking about. Okay, so it's a Diffie-Hellman key exchange. So let's talk about what the heck that means, and explore what's going on in this challenge. So we're not going to bring you all the way to the solution, of course, but we're at least going to talk about it at a conceptual level, because not seeing any questions in the chat, and I'm seeing a whole lot on the Discord about people talking about level 6. So which button? This one. We want this guy. Let's see if this works. Cool. Oh no, all of my stuff I forgot. How do we get rid of all this? Get rid of that. Oh, no, we don't do that. Hide status bar. Get rid of that thing. Get rid of that. Get rid of that. Can I get rid of this thing? Menu. Oh, that's not the one. Oh, this guy. Cool. That. Cool, 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 cool. And let's go ahead and how big is this font? It's not bad. This font size readable? Let's see if anyone says anything. Hopefully this font size is readable. Terminal fonts. This looks pretty good. 30. And what's our other font size? 30. All right, we'll just roll with that. Okay. So let's quickly take a look at the slides surrounding the Diffie-Hellman key exchange. And the slides and of course, the lecture video as well kind of conveys the whole idea of this key exchange. So the purpose of this key exchange is, as the name conveys, is to exchange two keys. Because one of the problems that occurs, for example, when we're talking about symmetric encryption, if we think kind of back to our very first example of cryptography, of encryption, we talked about the one-time pad. And the issue with the one-time pad is it's like so incredibly useful, except in order for it to actually be useful, you need to exchange a key that is as long as your message. And then the question is, how do you exchange this key that's as long as your message? And what's the point? Because you can only use it one time. Like, why not just exchange the message? I guess in some sense, if you have a different communication channel, you could pre-establish, share, 10,000 bytes worth of one-time pad, and then at some future date, if you securely do this, maybe by physically or something, right? We say, hey, if I do a USB pass-off, I hand you this USB, and on it is a 10,000 byte file that has the one-time pad we're going to use in the future. We consider this maybe channel secure. Well, then in the future, I can use that one-time pad to communicate with you, and things are cool. Now, this isn't really going to work so great if you don't have access to some sort of trusted channel. The next issue, of course, is that you need a one-time pad that's just as long as however much data you will be conveying. We looked at AES a little bit, and AES solves this by having a much smaller key. We can have this single, 20-byte key, and we can use this to exchange thousands and thousands of bytes of information without issue. Again, though, the question is, how do we exchange this key? The key exchange, there's different methods for going about doing it. But this, of course, the key exchange addresses that problem. How do we exchange that key? So in this example, we've got this paint exchange just to kind of get you mentally prepped for what the heck are the underlying ideas involved here. And you can see here right at the start, we've got paint. We're using this paint example. We've got Alice and Bob who are trying to share a key. And we have this presumed malicious Mallory off on the side watching this all unfold. And we need to do all of this, this key exchange under the assumption that Mallory exists, that there is this malicious person, right? If Alice and Bob were just to say, hey, the key is blah, Mallory hears that. So this is what we're trying to avoid. So for example, here, they both exchange this yellow paint. And so Mallory knows about this yellow paint because in public, they just transferred between each other this yellow paint. Mallory's watching everything in public. Yellow paint was exchanged. Now what Alice and Bob go and do is they each come up with their own color. So Alice comes up with this orangish color, Bob comes up with this bluish color. At this point, they haven't exchanged their colors in public, so Mallory doesn't, for example, know about those colors. But of course, Bob doesn't know about Alice's color either, and Alice doesn't know about Bob's color. So there's really not information exchange. We've just kind of privately done this creation of a color. And now what Alice and Bob do is they mix their respective paints with that original yellow. So they have a new color. Again, Mallory does not know about this new color that Alice has, or the original, or this private color. Mallory does know, again, about this initial color. And similarly, Bob doesn't know about Alice's new color, right? This is kind of conveying who knows what, right? Mallory knows about one color, Alice knows about three, Bob knows about three, etc. What they do is they actually exchange these paints, and hopefully it's clear, right? We're exchanging in the public. Guess what? That means Mallory knows about these paints. Now, Bob also knows about it. Alice knows about it. Right now, we have these paints. Still, Alice has this private paint color, and Bob has this private paint color. Mallory has 3 of the 5 total colors. Alice has 4 of the 5. Bob has 4 of the 5, a different 4 of the 5. Right, we kind of just have this strange-ish mechanism that just occurred that's maybe non-obvious why this is interesting, but something just occurred here. And what occurred here is that Alice can now mix the private paint that only Alice knows about with that mixed paint that Bob sent, right? Bob mixed these two to create this color, he sent it along to Alice. Alex mixes this in, Bob mixes this in, and suddenly we have this brownish color, and it turns out that Mallory just doesn't know what this color is. But now Alice and Bob know what each of these colors is. And so kind of the assumption is that even though Mallory has this color, the kind of presumed assumption under this scenario is that it is very difficult for Alice or for Mallory to subtract this yellow color from here and to subtract this yellow color from here, right? If we think back to the beginning, right, yellow plus red made this orangish color, and yellow plus blue made this other blue color. And if you could subtract paints, then, right, this would not work, because then Mallory could just subtract this yellow from orange, because Mallory knows the entire scheme that's going on. It's not just that Mallory got all of this data, but Mallory, we also presume, knows the entire scheme that Alice and Bob are doing right now. And so if Mallory could go and subtract yellow from orange and subtract yellow from this blue to get back to those original private things, this whole scheme would not work, because then Mallory would have this private information and would be able to reconstruct this color as well. So we're kind of assuming that that operation is difficult. That's kind of the presumed assumption, is that adding paints together is straightforward. Subtracting paints is not. Okay. So that's the property we need. So blah, 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 math stuff, math stuff, math stuff. It turns out fancy math stuff can get you something that mimics this property of being able to mix paint together, this kind of idea, and similarly encapsulates that idea that that adding paint together is easy, subtracting paint is hard. That's kind of, we need that property encapsulated in math somehow. And it turns out that you can achieve this property. So we work in this, it turns out with a lot of crypto, you work with some kind of maybe non-obviously interesting math constructs. In this case, we're working with this number system that's mod 13. So that means there are a total of 13 elements normally. So here, right, we're working with n mod 12. So there's 12 elements. You can kind of think of that as a clock. Turns out if we do this like 7 to the n mod 13 rather than just n mod 12, turns out there's also just 12 elements. Even though it's mod 13, there's still only 12 elements here. And the reason for that is that if we take 7 to the 12, it turns out that that also maps onto 1, as does 7 to the 0. So both 7 to the 0 and 7 to the 12 map onto the same numbers. That's why it's that 13 kind of gets reduced to 12. This is just a mathematical property when you are taking the modulus of a prime number. There's other properties of non-prime numbers, but in this case, you'll see that this is, in fact, how it works. We're not going to get too deep into the math here. And we can start doing this kind of additive thing, and we can kind of think about the corollary subtractive thing. And so what we can do in this numbering system, where we kind of imagine that 1 is equivalent to 1, which hopefully that is very clear on this side of maybe just that normal clock, right? That 1 is equivalent to 1. On the other hand, 1 on this side, right, where if we plug in n equals 1, you think 1 o'clock, that is equal to 7. So 7 to the 1 mod 13 is equal to 7. Similarly, we have 5 is the same thing as 5. Hopefully that's clear. And 7 to the 5 is equal to 11. If we look at 5 o'clock, it is 11. We've got negative 2, for example, is the equivalent of 10 in this 12 ring. And you can kind of think about that as just walking backwards. Or if we start at noon or midnight or whatever and walk backwards to, that this is 10 o'clock right here. Similarly, if we do 7 to the negative 2, mod 13, that is equivalent to this 4. We've got like this weird distorted clock, right? And it turns out we can also do not just like represent numbers in this system, but we can also represent, more importantly, things like addition in this system. So for example, 1 plus 1 is 2, 2 plus 2 is 4. Similarly, 1 plus 1 in this 7 to the n mod 13 thing is equal to 10. So just as you'd expect, the 2 o'clock is the 10. 7 to the 2 is, yeah, exactly. Hopefully this is all clear, even if it's non-obvious that this is in fact true. We can start doing things like multiplication as well. And so what Diffie-Hellman key exchange relies on is this, like, you can think of it conceptually in your head as this weird distorted clock math, except it might not necessarily be 12 numbers on our clock. We might have millions of numbers on our clock. All that really matters is it's some number to the n mod some other number, or more. We'll kind of see the properties of that here in a second as we translate that more into Diffie-Hellman key exchange. Again, don't worry too much about the math. The math is critical in that it's what makes this work. But if you want to understand, kind of sit down and do some algebra, right? Okay. So Alice and Bob, the way that this all goes down is that Alice and Bob publicly agreed to use a modulus p and base g. So we've got this base number g. So in this case, right, we had base of 7. In this case, we're just generalizing that 7 to be a g. And there's also some mod p. So in this case, p is 13, g is 7, right? So these are kind of these numbers that exist as kind of just Alice and Bob publicly agreed. If you think about this, publicly agree, that means that Mallory knows about this number as well. Okay, so hopefully it doesn't sound too arbitrary, but if it sounds arbitrary, just roll with it. We'll see how this unfolds. So Alice chooses a secret integer a, then sends Bob the capital A, such that capital A is equal to g to the a mod p. So we're using this publicly agreed g and p. We have this secret lowercase a, and from that now we can all derive uppercase a. Similarly, Bob does the same thing with lowercase b and uppercase b. And Alice computes this S, which is, I forgot to mention, sends Bob uppercase A, sends Alice uppercase B. If you think about it, Mallory now also knows about uppercase A and uppercase B. Alice computes S, which is take B to the A. Bob computes S, which is A to the B. Alice and Bob now share a secret S. So hopefully it's kind of clear that this is very similar to that paint exchange idea of we got this private information, this secret information. We're doing these mathematical operations. Instead of paint mixing, we're doing modular exponentiation. And we can see that the math all works out, that if we have this g to the a mod p to the b mod p, that's the same thing as g to the ab mod p, which is the same thing as g to the ba mod p, which is the same thing as g to the b mod p all to the a mod p. Which, it's a mouthful to say that, but the algebra is really not too difficult. Hopefully that's clear that these are, in fact, the same S. And so if we look at this here, we share our G and our P numbers, this public numbers that we're going to work with. Alice and Bob find some number for themselves. We perform math. We share. Mallory now knows these shared numbers, but we can finish out the math and get our secret number. And as I said before, we kind of relied on the paint mixing to be secretive, right? Or excuse me, not secretive. The paint subtracting to be difficult. Well, it turns out that kind of going backwards on this clock thing, that figuring out that 5 is the same thing as 3 o'clock is difficult. This is called the discrete log problem. So I might communicate to you the number 3, right? And the fact that we know that that's 8 o'clock, right? That 3 actually lines up with this 8 o'clock on the clock. There's no easy way to do that. There's no way to reconstruct capital N given the result of this operation. This is called the discrete logarithm problem. Now, that doesn't to say that it's impossible, right? For example, one solution to performing this subtractive operation is to go through and construct this clock, right? If we go through and we do 7 to the 0 mod 13 is equal to 1. And so now we know that our 0th position on the clock is 1, which means now we know that if someone says 1, it's the 0th position. Similarly, we know this 7. Of course, these first two are actually kind of trivial because we know that 0 has to line up with 1 because 7 to the 0 is 1. Similarly, 7 to the 1 is 7, right? These ones are easy. Once you start hitting this mod, which the rest of them do, it's not easy to go back. So if I tell you 10, there's no good way to know what the original n was. We can go through, though, and compute all of these values. And then if I say 10, if I've computed it all, and I know that the thing that I initially put in to create 10 was 2, well, now I can say, well, 10 is 2, and go back to 2. And if you can go backwards, it turns out that's the equivalent of subtracting paint. And since it's difficult to do this operation, not impossible, right? We could brute force solve all of the things and now have a backwards table, lookup table to solve all of this. The fact that it's difficult is good. Now, realize, of course, that we're working on this 13 number clock. Brute forcing 13 elements, or really 12 elements, is very straightforward. We can construct all 12 of these things, have our lookup table go backwards. The question is, what happens when this is a multi-trillion number thing, right? You could build this lookup table up until your computer literally just can't store enough things. There's no way to do this lookup table. And crucially also, it's not that we're always using the same, is that true? I was going to say it's not that we're using the same GNP, but I believe we are actually always using the same GNP in standard implementations of Diffie-Hellman. Technically, you don't have to. We'll see in the challenge what numbers we're using. I believe we're using some numbers from some RFC that says, hey, use these numbers. You could imagine using different numbers, though, if you're really worried about this lookup table. existing, but it turns out these numbers are so large, it's just you can't build this lookup table. It's infeasible. Okay, so going backwards is hard, which means we're good to go. Okay, let's double check if there's any questions. I don't really get the difference between user certificate signature and user. Okay, well, that's a different challenge, but we'll get there. Sorry to be off base. Do beginner stuff. I'm just getting started. We do have beginner stuff. Look on the website. There's like a getting started module. Check that out. Ask on the Discord. Would be great. Okay, let's look at this challenge though. So if I look at, well, let's actually just run it. We don't need to look at the source yet. You'll see that what happens here in this series of challenges, you'll be blah, 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 working with Diffie-Hellman key exchange. We'll see that I just got told this P value. Actually, I am going to look at the challenge real quick. Code server challenge level 6. Yeah. So you'll see that RFC 3526 talks about Diffie-Hellman. Okay, and they just like say use these numbers. And very popular is people listen to this, just use these numbers. There's various, I honestly don't know the deep-rooted issues that well, but I'm vaguely familiar with the fact that if you're not careful with this P and G numbers, that doing this backwards operation can become easier for certain numbers. There's weird properties. This is kind of something that cryptographers look at, and they figure out these weird properties of all these numbers. So for example, in Diffie-Hellman, that these P and G numbers really need to have a whole bunch of interesting properties to them. It's not like we're just picking two prime numbers, for example. There's other properties involved. And some numbers are maybe non-obvious on why they're weaker. Just honestly don't understand it too well. I'm sure you could search around, or I'd be happy to search around if there is interest in further understanding why these numbers. But this is really the realm of proper cryptographers figuring out that, hey, these numbers don't appear to be weak in these ways we've kind of considered. That makes it easier to do this backwards operation, because we cannot allow the backwards operation to be made easier. Ideally, this backwards operation is as difficult as possible. Ideally, it's on the order of like you just need to brute force look through all of them. And if this is a very large number, of course, right? See, this is a very large number. On the order of 2 to the 1536 of a large number, that, yeah, we need to make sure that it's not, or this is even for that. I think we were using the 2048-bit numbers. Okay, cool. So anyways, we have this P that's just defined, and G, again, taken from the RFC. They just say, hey, use this as P and use this as G. So it turns out, right, that this P number does need to be a prime. That's why they say that this prime is that we're using here. The generator has some other mathematical properties to it. Basically, the important number for that G generator, if you're curious, is that it needs to not have collisions. It turns out that if you use the wrong number, you could have collisions in these schemes. You want it to represent such that you put in an n. For every n, you get a different output, with the exception of this like 0th element, which also lines up with p minus 1. So 7 to the 0 and 7 to the p minus 1 to the 12 are the same thing. That's fine. But every other number needs to not come up with its own thing. So for example, you could mess around if you wanted to and see what happens if you use like 4 instead of 7 here. You'll see that this collapses. It doesn't have that property. Okay. some very fancy math stuff that I'm sure people discovered hundreds of years ago and they thought, wow, this is cool. This is almost like a form of art. And then it turned out to actually be useful. And here we are. Okay, so we're just declaring this to be the P and the G. And you'll see that A is just random, right? We just come up with a random number. And we'll see that when we run the challenge, what we're doing here is we're performing a key exchange. So we know P and G just right off the offset. So does Mallory. Mallory also knows P and G. And then we are told capital A. So Alice has communicated the public version for this key exchange, capital A, not lowercase a, right? If we look at this here, lowercase a is this random number. Uppercase is doing this G to the A mod P. And we are told uppercase A, not lowercase a. This has to be private. Then it's up for us to communicate uppercase B. What does that mean? What that means is we need to come up with a random number, right? Some random number. And it needs to then what we do is do this operation of 2 to that random number mod P, right? So we would do that. You'll see that the challenge also checks that you're using a sufficiently large number. So that B that comes out better be at least 2 to the 1024. Think about it, right? Alice is doing this correctly and doing a 2048 bit number. Really, B should be on the order of 2048, but we're just sanity checking, hey, this better be at least 1024 bits. Otherwise, you are not picking a very good number. And then what's going to happen, as you might expect, is that at this point in the paint exchange, we have exchanged a key sufficiently, right? I would have just now, we just would have completed this. So I have Alice's uppercase A. I just transmitted to Alice my uppercase B. Now we can both compute S. So we'll see here in the challenge that you kind of think of this function as representing Alice doing her side of the thing. Alice computes S. It's also up for us to compute S, which generates a key. And then we actually just, in this case, this is a very common cryptographic scheme in total, but we actually just use that key as a one-time pad. Normally, you wouldn't actually do a key exchange for a one-time pad in this way. It just isn't a typical thing. There's no reason you couldn't necessarily do it. It's just normally we might move to something like AES at this point. But in this case, we keep it nice and simple. We use the key, we compute this key. Now we use it as a one-time pad. And Alice is going to send us the secret ciphertext, which is a one-time pad using that key of the flag. So now, once the secret cipher, so basically Alice shows us uppercase B, we give Alice uppercase A, and she sends us the secret ciphertext. So at this point, we should be able to uncover that. And the way we do that is we just do this math, right? And in fact, I would encourage you not to maybe think too hard about how to generate a 2048-bit number. Just do it the same way Alice does, right? We don't need to complicate this. So for example, if I grab this function here and I look at IPython and I do get rand bits 2048, I've got my lowercase b number, right? B would equal this. And then do the operation, right? So level 6. Do this PAL, right? G to the A mod P. So you're going to have to grab this, right? So we're going to have to parse this out. We'll say P equals this thing. G equals 0x2. We could just say 2. And then what I can do is B, let's not overthink this. GAP instead, GBP, right? And now this is the number that I would be sending to Alice, right? When it asks for B. Of course, we should keep the same scheme. In fact, maybe this is something that's tripping people up. We want that to be in hex. So, in fact, I'm curious. Hex. Yeah. Give it in hex. Which hopefully is not too difficult, right? We just do hex of that thing. Right now we've got our hex number. Send this along. In fact, I'll just show that real quick. Every time we run this, Alice is going to come up with a different capital A, right? So this one is H2. This one is 3B. That's fine. G and P, or P and G, are the same thing. Technically, now I can send this along, though, right? And send that along, and you'll see that we get secret ciphertext, which is clearly base 64 encoded. We also want to decode this as base 64, which we've learned in previous levels how to decode a base 64 string. Take that, compute our S, right? We have all the information necessary. We know lowercase b. We can use lowercase b with uppercase a to derive the secret one-time pad, apply that against this once base 64 decoded. Should be good to go. Okay. So someone is asking, I don't really get the difference between user certificate signature and user signature. So I believe this is talking about the last level. Is it level 11, level 12, level 13, level 14, level 14? Okay. So can I zoom? I can't zoom out. I'm going to zoom out a little bit. Hopefully this is... I'll zoom in one more. Now we'll zoom out one more. Okay, hopefully this is at least kind of readable. I highly encourage people, especially as they reach level 14, but possibly even earlier, to go into the challenge and read the source code. So for example, as I was just doing for level 6, I was reading the source code of level 6, and it kind of maybe can clear up any confusion. In the same way, I highly encourage people to read the source code for something like level 14. So we'll see that this is the output that level 14 tells us. It says, hey, we're basically doing a TLS handshake. So whenever you go to https:// that HTTPS, the S part of the HTTP, we already learned about HTTP. That S portion of it is the TLS portion of it. This is what makes it actually cryptographically secure for me to go and talk to pwn.college and send my username and password. I'm not sending that in the plain text. It's all happening cryptographically. And this isn't exactly TLS. It turns out TLS has a whole lot of extra features, I guess is probably the simplest way to say it. But this is the core essence of a standard. Like this would be very valid of a way of doing it. This is just more simplified. There's other kind of small little concerns, but this is the core idea of that handshake. So as we'll see, we got a lot of stuff going on. It turns out like all these previous levels kind of are really coming together in level 14. So if we look at this source code, we'll see we've got P and G, which as we were looking at level 6, it's going to be the same P and G. So the challenge is going to show to us P and G. It's going to generate a random number, okay? Random, and we didn't look at RSA in level 6 because level 6 isn't about RSA. Previous levels talk about RSA. We generate a 2048-bit RSA key. And let's see here. You'll see that it shows to us root key D. So this is actually under a normal scheme, non-standard. You normally would not be told root key D. This is a very secret, sensitive piece of data. But for the purposes of performing this handshake, I believe we're acting as the server. Yeah, we're acting as the server. So we're kind of assuming that this is our sensitive information. The challenge just generates it for us. We have this root certificate thing, which has a name. It has a key, which has, once we know about RSA, this public portion of the key is E and N are the two public parts of the key. We say who's signing it, and this is really it. So we're saying signer is root, name is root, the key is this. And root trusted certificates, we'll have to figure out what the heck this is. We have this root certificate data. So we JSON dump this thing. Then we SHA-256 hash this thing. So we hash the certificate. Okay, and then we sign the certificate. So whatever this root certificate data thing is, this thing is getting JSON dumped. That thing is getting hashed, SHA-256 hashed. And then that thing is getting signed. And the way that we sign that is, as the previous level talks about, the way that you sign something is you take something and you raise it to the private key mod n. So this is the definition right here of a signature. And we're signing it specifically with the root key. So you might be thinking some things here. There's actually, this is maybe slightly strange. We're kind of signing this root certificate with the root key, which is like, what does that prove? Well, it doesn't actually prove anything. The signature kind of is almost meaningless. It is the root certificate, though. It is a self-signed certificate. So a self-signed certificate doesn't really, as I just said, mean a whole lot. Other than, I mean, basically what we're able to convey through doing this is that, that someone has the private key of this thing. It doesn't really matter that much. It's just very common that to use a root sign or a self-signed certificate for various purposes. This is a self-signed certificate. So I'm basically saying I trust myself. That's like really all a self-signed certificate means. And it's kind of like obvious-ish, probably. I don't know, you get real philosophical with it. But if we think about this root of trust thing, probably every individual entity can assume it trusts itself. Probably. I don't know. Maybe there's a world in which you don't want to operate with that assertion. But what we're saying here is that root trusts itself. It's kind of what this mathematic construction is conveying, which is kind of, it's kind of pointless, but it's beginning the chain, right? We're starting by saying, I trust myself. And then the next thing we're going to do is, and I also trust blah. And now if you trust me and you trust the people that I trust, you can convey that trust through. Okay. But probably if you trust me, you also trust that I trust myself. So I don't know. Think of that as you will. It's not, I don't know. You get real philosophical and maybe it's deep, but it's really not that deep. Okay, so we then output the root certificate and the root certificate signature. So the root certificate is literally just this JSON dumped thing. This thing. So it's going to be base 64 because we're conveying a lot of data with base 64. You just base 64. So for example, to make that real, well, I can't run the level actually right now. Oh yeah. So if you're not looking at the source code, this is the way to do it. Hopefully this explanation of things will really clear things up in case you're like, what the heck's going on in this source code? Okay, so we're being told the root certificate, which makes sense. Basically the challenge, we are the server, but the challenge is kind of helping us along in being the server as well. So we are the server. The challenge also is kind of the server because it's telling us our root certificate. And in theory, we're doing a handshake with someone who isn't the server, some client, which is also the challenge. The challenge is like 100% of the client and like 10% of the server, and then we're the other 90% of the server. Okay. So we get the certificate, we get the root certificate signature. Again, this is just saying I trust myself. The important thing, though, that we're conveying to some client, for example, if we were to give this and present this as the server, we were to present this to the client, what we're saying is, hey, my public key, if you want to talk to me, my public key is E and N, right? The E and E and N, think back to RSA. This is the public portion of the key. And so the client can now look at this and again, it's just like this root of trust. We're just like already the client has kind of assumed to trust this root authority, let's say. But it's a self-signed certificate, blah, 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 blah. Okay, anyways, let's keep rolling with this. Then the challenge constructs some random name. It's literally just 16 lowercase ASCII characters, and this is the name. It shows it to us. Here is 16 random lowercase letters. That's our name. It's not a very exciting name, but that is the name. Then the challenge constructs this lowercase a thing. Think back to Diffie-Hellman. This is the same lowercase a in Diffie-Hellman. Constructs uppercase a by doing g to the a mod p, and it shows to us this uppercase a. Then we do a Diffie-Hellman key exchange, just as we did in level 6. We provide uppercase b by doing the same thing. We have a lowercase b, 2048 bits. Do g to the b mod p, offer that up. Now we have a secret shared, right? The secret is shared. Okay, and then we have, what this line is doing is it's taking this s. This s normally is just like an integer. We're converting that integer into bytes. And also we're taking the hash of those bytes. So we're just taking an integer, converting it into bytes, hashing those bytes. And then taking the result of that hash, at least a portion of it. And now we're using that as the key. Okay, so maybe you think of that as arbitrary, whatever, I don't really care. We just converted S into a key by using this scheme here. And this is something that if I have S, you have S. The scheme is known. We can both convert into a key. Here we go. Now we build up this AES object, which is using this key. And we build up this like cipher encrypt, cipher decrypt. It's actually the same thing. It's just now we have one thing that's tracking this for encryption, one thing that's tracking it for decryption, because we're going to go down this chain. We'll see, but it'll make sense here in a second. We're specifying IV equals this, blah, 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 blah. Okay, cool. Then what we do is we decrypt input base 64. So what's going to happen now is that the challenge is asking us for a user certificate. So the way that this is going to happen is it's going to take in base 64 of this user certificate. And it's going to decrypt it using this AES construct thing here that's based on the key, based on the Diffie-Hellman key exchange. It's taking this base 64 and decrypting it. That better mean that when you send it, you should have sent it encrypted, right? You will have sent it, because once you've done this Diffie-Hellman key exchange, we're talking over AES now, because we've got a key. We're trying to be cryptographic here. We're talking over AES now. Okay. We unpad it because we got this whole padding thing, which previous levels and the lectures talk about. We unpad this thing. Very cool. We then decrypt it. So that means what you're going to do is you're going to encrypt something and then base 64 it and send it to the challenge. And then the challenge is going to debase 64 it, decrypt it. And now it has this thing which we're calling the user certificate, or specifically here, this part, user certificate data. Then we're also sending a signature. So then the next thing we're going to do is we're going to encrypt the signature, base 64 encode that encryption, send that to the challenge, and then the challenge is going to debase 64 it and then decrypt it. And finally, we're going to send also the user signature. So I guess this was the initial question, was like, what the heck is the user certificate signature versus the user signature? Well, we're about to find out what the heck it is by looking at this source code here. So now we have this user certificate, which turns out to be JSON, because the next thing we do is we take this user certificate data and we JSON load it, which means now it's like a Python dictionary thing or whatever it is. We can work with it in the same way that this thing initially was like a Python dictionary thing, and then it got JSON encoded. Now we're JSON decoding it so that we can start accessing elements of it. And if this fails, maybe you've already seen this in your challenge, you get invalid user certificate. That means is that you did not JSON dump a user certificate and then encrypt it using this key, which you would be able to derive because you did the Diffie-Hellman key exchange. So you know S, which means you know key, which means you can encrypt it, and then base 64. So there's a lot of things going on. You JSON dump it, then you encrypt it, then you base 64 it. Okay, and then the server is going to do, or the challenge is going to do everything in reverse. So that's how you make sure that you sent something. Now we're going to check more things to see if it's a valid user certificate. There better be a key in this dictionary thing called name. Otherwise, it's going to say invalid user certificate name. Or specifically, it needs to be equal to the name that it showed to us. So it generated a 16-character name. This user certificate thing better be those 16 characters. Then we investigate the key, and we look at E, and we look at N. These things better be integers. Okay, E and N, same way that this thing right here, E and N, are integers. The thing that you sent off better have a key with an E and an N, and those things better be integers. Specifically, E better be greater than 2. If you don't send an E greater than 2, you're not doing RSA very well. It can't be a negative integer, it can't be 0, it can't be 1. E had better be greater than 2. And if you construct an RSA key correctly, it will be greater than 2. N had better be between 512 bits and 1024 bits. So what does that mean for you? Well, I mean, really the simple thing here is to just generate. I mean, I think if you do RSA.generate like 1024, this will work just fine, I believe. But it'll warn you if your N is not in the valid range here. Okay, then we've got a signer. So we grabbed the name portion, investigated that, and grabbed the key portion, specifically investigated the E part of the key portion, the N part of the key portion. Now we're looking at the signer portion of this certificate. Again, kind of think of it as it's looking very similar to this. It's just the name is different. The key likely is different. The signer is, well, we're about to see what the heck are the properties of this signer thing. Well, the signer needs to be in the root trusted certificate. So the person that signs off on this user certificate needs to be a root trusted signer, basically. So you'll see right here that inside of root trusted certificates, there is one thing. This is the world of trust. This is who I trust, and I trust this person to trust other people also. So I trust root to trust other people. This means is that this signer had better be root. So the person that signs this user certificate has to be root. Turns out you have all the information. Well, we haven't even gotten to confirming that root correctly signed it yet. But the certificate at a minimum better say that root signed it, and then we'll confirm that that worked correctly. Right? You could imagine that we say root signed it, but root didn't actually sign it. And we'd be good to go still so far. As long as it says that root signed it, we're good to go. Technically, this still isn't a valid certificate from a trust perspective yet, because all it says is that root did sign it, but did root actually sign it? Is what we're about to investigate. So then we take the user signer key, which is go into our root trusted certificates, grab the user signer, so this is going to be root, and grab their key. So we're about to grab that person we trust, root. We're going to grab their key, and we're going to verify the signature. So it turns out that what was something else we sent, right? We sent the user certificate signature. This user certificate signature, it had better be root that signed that thing. So Where did that go? Yeah, so what are we going to do? We're going to take the user certificate data. So the user certificate data, not de-JSONified or whatever. Like we haven't, user certificate data is subtly different from user certificate. One has been JSON loaded. One is still just a bunch of bytes. We're going to hash that bunch of bytes, and then we're going to check the following. Well, so specifically then what we're going to do is we're going to take this hash, we're going to take the user certificate signature, which was the second thing we collected after the user certificate. We collected the user certificate signature. We're going to take that thing as an integer, raise it to the e mod n, and that thing here, so the signature raised to the e mod n had better equal the hash of the user certificate data. Okay, so the signature to the e mod n had better equal the thing that was signed. Right? We signed the hash. We always sign the hash because you can only sign so much data. So you sign the hash, and we know that hashes are non-collidable. Hashes have these properties. That's why we can sign the hash and still feel confident about it. The hash of that certificate had better equal this. I mean, this is how you verify a signature, right? You check the signature, you raise it to the E, which is the public thing, mod n, also part of the public thing, that had better equal the thing that was signed. This refer back to signatures if you're wondering, like, hey, what properties does that get us, right? This is how you confirm a signature. So we're right here, we're confirming that the signature is good to go. Otherwise, if it's not good to go, we say invalid signature. You have all the information necessary to sign this thing, because guess what? As I said at the very start, we give you right all the way up here, we give you root key D. This thing right here is what you need to be able to sign it. And then you also know E and N because we tell you E and N through this certificate. But this is the crucial bit of data that allows you to sign something. So sign it correctly. Okay. Now let's keep rocking and rolling. What else do we have here? So the next thing we do is this user signature data is going to be the name, L justified, so left justified by 256. Basically, we're extending the name to be 256 bytes, where on the right is a bunch of null bytes, right? So if you're ever confused about like what the heck is this Python doing, just start running Python, right? So if we look at this real quick, if we imagine the name was like, let's see here. Why is this? I feel like my computer's lagging. Okay, we're gonna look at that in a second. L just 256. Am I lagging or is the server lagging? That's the question. Either way, this is what that sort of thing does. Always just run Python if you're confused what the heck this is doing. It's just extending it so that it's 256 bytes. Okay, let's keep rolling. And then we're also concatenating uppercase A. Think back to Diffie-Hellman, I believe, right? That's where that is coming from. There's the Diffie-Hellman stuff. Uppercase A, uppercase B. That is also ending up in here. Uppercase A, uppercase B. Honestly, why? I'm not so sure yet. We're going to see what the heck that gives us, but for sure this is in here. So we have the name padded to 256 bytes. We have uppercase A from Diffie-Hellman stuff padded to 256 bytes. We got uppercase B padded to 256 bytes. Then what? Then we hash the user signature data. Okay, and then the user signature, which I believe is that third thing. So there's the user certificate signature, which we already saw the properties that need to hold to continue along, versus this user signature. It looks like the user signature is following this scheme, that we're going to take the user signature data, which is the name, A, and B, all hashed together, right? So that this hashing had better equal the user signature to the E mod N. So again, this is a signature check. We're checking that the signature is correct. And specifically, if we look here, before we were looking at user signer key, which user signer key was based on the signer, which is that signer field, which is going to be root because we already said root is the only person we trust, so root's the only person that could sign this thing. Roots E and N are used to verify this. However, on this side of things, user keys E and N had better be signing off on this thing. So what does that mean? Well, we sent a user certificate. That user certificate includes stuff like a key, which is going to be different than the root key. It's the user key. The user key is expected to have signed this blob of data. The name as 256 bytes, A as 256 bytes, B as 256 bytes. We need that signed. Okay. And if it's not, we say untrusted user, invalid signature. And then what do? We take the flag, we pad it out, and we encrypt it. We send this as ciphertext going off of all the way back up here when we used the key to generate a cipher underscore encrypt. Here we finally encrypt the flag. So you might be wondering, like, what the heck is this? Why do we even do this? Maybe the other stuff is clear, maybe it's not. In this part, we're establishing trust of the user certificate. The user certificate needs to be trusted. We will trust it if root says they trust it. If root says they trust it, now we can trust this thing. What this is doing is it's tying back in the Diffie-Hellman even more. And it's specifically, okay, it's a little bit subtle, with all the properties that we're getting by doing these operations. There is a little bit of a concern here. So you always have to be thinking about Mallory. So when we did this Diffie-Hellman key exchange, there is nothing stopping, let's see here if I can create a new untitled text file. Okay, cool. So there's nothing stopping Mallory from man-in-the-middling us, right? This can always be the case. So you can imagine the situation where we have Alice who wishes to talk to Bob. The concern is that Mallory jumps in there and man-in-the-middles, right? So that Alice is really talking to Mallory, hoping that they were talking to Bob. Turns out you're not. And then Mallory talks to Bob. And basically, if Mallory was just chilling, Mallory could pass all of this through, right? So Alice wants to send uppercase A, right? Alice wants to send A across to Bob. Mallory gets to see it, and now Bob has it also. Likewise, Bob can have B and wants to pass it along. Mallory sees it, and now Alice has it. This is totally fine. This is what the Diffie-Hellman key exchange is cool about seeing and has no issues with. Except it does, okay? This is where the Diffie-Hellman key exchange actually can have some issues. And I believe we talk about it here in this trust lecture here. There is a concern of, let's see, I don't have it, of basically two key exchanges being set up. That Mallory actually takes an active part. That Mallory doesn't just pass along B and pass along A, but instead Mallory becomes an active participant. So rather than just passive, active. And so Mallory does a key exchange with Alice and Mallory does a key exchange with Bob. And now Mallory, of course, knows the private key with Alice, and Mallory also knows the private key with Bob. And so if Alice trusts this key now and starts communicating, Mallory can decrypt this stuff, re-encrypt it using the Bob private key stuff, and send it along. And now we can keep passing all the way through. What this does right here, this subtle little portion right here where we sign this thing. What this does is it guarantees that the secret that I'm communicating on before I fully trust it is being for myself, right? The user, right? Don't think of the root certificate, think of the user certificate. So, right, Alice might be forming, or let's think of this as Bob is the server, right? Alice is the client, for example. So Alice trusts root. Root trusts Bob. So think of Bob as the name, right? It's really a 16 random character name or whatever. In this case, Alice trusts root. Root trusts Bob, which means Alice trusts Bob is kind of the conveyance of that, right? Really, it doesn't have to be, you kind of can broaden what does this trust actually mean. Really, what we might say is instead of just trusts, we could say Alice trusts root. Root declares Bob's identity as having this key. Alice knows Bob's key, right? So we trust root. Root says this is Bob's identity. This is Bob's key. Now Alice, because Alice trusts root, Alice knows Bob's key, which is great. However, this entire time we were communicating over this secret, right? We defined S as coming from this Diffie-Hellman key exchange. We don't actually know if there's someone in the middle here that derived this secret S, because Mallory could have been actually the person that derived this S, right? Mallory might know S because Mallory might know B, right? Because Mallory is the person that generated lowercase b to create uppercase B and is actively man in the middling. When we do this, right, Alice doesn't know. Alice now knows Bob's key according to root's trust, right? But Alice can't actually trust S. Alice still doesn't trust S as being defined by Bob, because nothing in this scheme yet has the properties that allows us to trust S. S hasn't been tied back into this key somehow, right? S is completely independent of Bob's key. So Alice still doesn't know that Alice is talking to Bob. All Alice knows now is Bob's public key. So we could switch over to a different scheme if we wanted to, and like use Alice or use Bob's key to start doing something. But actually what we can do is just have Bob sign off on S effectively. So Bob can sign A/B. If Bob signs A and B as being kind of as correct, really it's like name/A/B, right? That's what we're signing off on. My name, A and B. Bob is signing this thing. If Bob signs this thing, Alice can confirm, because it's a signature, Alice can confirm Bob signed name/A/B. And then what Alice can do is, because Alice knows name, Alice knows A, Alice knows B. These are all public information. S is secret, and should be secret from Mallory, unless Mallory did this man in the middle thing. But if Bob is willing to sign off on this thing, that means that Bob has asserted that S is safe in doing this. So if Bob signs this thing, we can know for sure that S is safe, which means we know our encryption key is safe, which means we can continue communicating safely. So this is effectively what TLS looks like. It's not good enough just to get Bob's key when we're already talking over this cryptographic S thing. We need to also, before we continue, confirm that S is safe. And this final signature is what says, okay, S is safe. You're not talking to a Mallory, because guess what? Mallory cannot sign this thing. Mallory is incapable of signing this because Mallory does not have Bob's private key, and you need the private key to sign this thing. We're good to go. Okay, so this is a lot of stuff going on and intermingling all of this math to create these properties. Ultimately, it works out. Okay, let's see here. What's going on here? The key comes from doing that S2 byte. Yes, exactly. So the key is defined. There's literally a key definition. The key is derived from S, where we take S 2 bytes. So we basically make this a 256-bit integer. If you're ever wondering what the heck does this do, think if we put 1, 2, 3 in here, this converted it into a integer. And you might imagine that S is actually, in fact, a much larger number. This is how we convert a integer to bytes, and we need bytes to be able to hash. Hashes don't go off of integers, you hash bytes. So this works great. Now we have a bunch of bytes. We put these 256 bytes into here. We hash this thing. We grab the digest, which is, again, bytes. We take the first 16 bytes. Now we've got a key. In theory, you could imagine just doing... In theory, you could imagine just doing the following. I don't know if it's going to let me out. Yeah, it does let me. You could also imagine that this is how you derive the key, right? This would technically work as a mechanism of deriving the key. It's just, I mean, what's the best way to explain this? I mean, the first thing you'll note is that this is a little bit weird, right? So we're making this be a 256 byte number, and then we're only taking the first 16 bytes of it. So that's a little bit weird. And this really is a 256 byte number. If we look at, if we think about, where is it? This thing right here, this P number, this kind of defines how big S will end up being, because everything's mod P. We're constantly doing mod P. This is a 2048-bit number, aka a 256 byte number. And it's just always awkward to just truncate a number like this. It just doesn't feel good. I'm not actually sure if there is, in fact, a weakness there. But whenever you want to truncate something, it's just like, it just feels safer to hash it. Because who knows if there's weird properties of these upper 16-byte numbers of an S defined like this. I don't know. It doesn't feel good, is I guess what I'll say about that. There's not like, we have this S number, which is a secret. Whenever you want to like condense that secret number, and we want to take like all of the entropy, all of the randomness of that number, all of like the essence of that number, rather than just like take a portion of it, that sounds scary because there might be weird properties sitting here in this part of the number. Like the entropy might actually be further distributed over here. I don't know how this math actually works, if that's true, or if we can say that all of the bits are random, like with equal probability. If you're ever like unsure, you just throw that through a hash function, and that's going to make sure that the entropy is evenly distributed across that entire set of bytes, that all of these bytes are now random goodness, rather than if there was a weird distribution across those bytes before, if we just did this, right? These first 16 bytes, I don't know. I don't trust them. That sounds scary. Just throw it through a hashing thing. That'll make sure that the entropy is nice and smooth throughout all of that. I guess that's kind of my philosophy here, how I would try to convey that. It's a very feelsy sort of thing. It's very just when in doubt of the properties of your data, hash it. It's kind of assuming you can get away with that. In this case, we can get away with that because both sides know S, right? Both sides can do this to derive the key. Yeah, exactly. What was L just again? Yeah, hopefully I demonstrated that. L just, it's padding these bytes to be 256 bytes long. What's the other stuff? What else should the other stuff be? It should be just zeros. So that's what's going on here. So as the user's private key, the E value, is the user's private key the E value? No, the user's private key is not the E value. Okay, so here's what I'll say about that. You get to make the user's key, right? Nothing about this is telling you what the user's key should be, with the exception that E had better be greater than 2. So you would be right on the money here if you decided that E was 65537 or whatever, right? The very standard number. E can totally be 65537. It technically doesn't have to be. It would be awkward and non-standard if it wasn't 65537. But technically the challenge isn't saying, hey, E had better be 65537. It's just saying it better be greater than 2. And then N needs to be between 512 and 1024 bits. Okay, here's the secret here. Okay, just do this. Okay, this is now user key. User key.E is the public thing. User key.N is the other part of the public thing. User key.D, this is now the private thing. Just use the same code in how we generate a key. Just do this. You don't need to be. You don't need to get fancy with how you generate it. Just use the same code. Okay, just rsa.generate. Except you can't do 2048. It's got to be 1024 because we checked that the max is 1024. If you're wondering why we do that, normally you wouldn't do this. I just wanted to make sure that you didn't reuse the root key. Is really all that this challenge is doing here on why it's a 1024-bit number. I wanted to make sure that you generate a different key. I guess I could have checked this, not the same thing. That probably would actually make more sense. I just didn't want you to turn around and once this was dumped to you, just send it back by just changing the sign or changing the name. Because in theory, otherwise, you could just take this root certificate and change the name from root to whatever the heck it tells you the name should be and send it back. And now both would have the same public and private keys, which there's nothing technically wrong with that, but I just wanted you to do more work. But really, the more work is just do this. Okay. Entered in late. In this challenge, you're acting as people sending a key. Yeah, so what we're doing here in this challenge is that I am pretending I am an HTTPS, emphasis on the S, would make uppercase S with like a arrow pointing up at that S server. The client is assumed to trust roots. To make this, okay, so there's kind of a few things going on in what is happening in this challenge. So the client trusts root. Okay, I'm an HTTPS server, the client trusts root. Normally what would happen is that the server would go talk to root, prove identity. For example, I mean, you could think of it as show my driver's license to root and ask them to sign my certificate specifically and ask root to sign my certificate, right? So we kind of are pretending the client trusts root. Why? Because they do. There's just baked in trust. I would go, so let's say I would go talk to root server, go talk to root, prove my identity, show my driver's license or whatever to root is kind of what you can imagine. Realistically, in a server scenario, you do like a DNS challenge that shows that you're in control of this IP address. Normally, the thing that you're really doing is you're tying a domain name, so like pwn.college, and if we look at ping.college, what we really need to do in HTTPS as, let's say, pwn.college, is this IP address. What we're trying to do is declare this as facts, so that when you go to HTTPS pwn.college, you had better be talking to this IP address and not some other IP address. So when I'm doing this identity stuff, I'm, instead of showing my driver's license in order to get this certificate so that I can be HTTPS, what I'm doing, and when I go talk to root, is I'm saying, hey, I control this IP address. Like, for example, you could imagine root says, okay, if you control this, actually, if you control pwn.college, and that is make it so when I curl, let's do this. So root says this, okay, if you control pwn.college, and that is this IP address, make it so that when I curl http /pwn.college/challenge, I get HTTP 200 content length 50 this message, right? Or like, you know, some challenge response thing, right? Like I better see this when I talk to pwn.college and hit this /challenge endpoint. I do a curl here. I better get an HTTP 200 content length 500 with this random bit of blah. And if you can make pwn.college do that, I believe that you are pwn.college and that you control the server. I am now willing to sign your public key. And so people that trust me know I said you are legit. Because you don't want to make like, you don't want to constantly have this challenge response. It doesn't even make sense, right? That you couldn't constantly be doing it. Because how do you know that you're talking to the real one? Well, this person does this challenge response thing. It confirms, okay, I'm talking here. I'm talking to this IP address. This is in fact the IP address that I'm going to. I got this. Okay, you're legit. I will sign your public key, aka certificate, aka pwn.college /e/n, right? And so people now trust you. Okay, so this is what's happening here. However, we kind of bypass this whole part. Maybe it'd be interesting to figure out how to integrate that into the challenge. Instead, we just say, you are also root because you know root's private key, right? Because we told you in the challenge root's private key. So you get to just sign it, right? Just sign it yourself. Okay, under normal circumstances, you would not be signing your user certificate. Some trusted person would be, but for purposes of this challenge, you sign it yourself. And so now what I get to do after I have this signed certificate, I have a signed user certificate by someone that the client trusts. I can pass that signed certificate to them so they can know my name / public key pairing, right? We need to just tie the name to the public key, aka pwn.college to some public key. And then also do this over a Diffie-Hellman and key exchanged AES session and sign that Diffie-Hellman key. right? And the way that we sign the Diffie-Hellman key is that we use this thing that's in this user certificate, and we sign A and B. This would just be awkward to sign S. That would be weird, right? This is all public information. Just sign the public information. If you can sign it, you're asserting that this is the correct stuff. It's presumed that if you're willing to sign off on this, that you also have S, because why would you sign off on this unless you said that this was actually the correct A and B, which means that the A is the correct A from Alice, which you received, and B is the S. B is what you define. Like, you're just asserting that this is correct. Technically, in this scheme, we don't necessarily trust the client. So this entire scheme offers us no trust about the clients, right? The client can now trust the server. The server has no clue who the client is and cannot trust them. That's fine. For HTTPS, for example, this is the property we need. We don't care about trusting the client. We'll build in that level of trust through HTTP cookies when they log into our website. It's like, if you have the username and password, that's going to be my trust mechanism here. It's like, all I'm talking to is someone with a username password pairing, and I don't care who the heck that actually is. We don't need to do this cryptography. Could imagine this fancy system that maybe somehow does public key cryptography instead of usernames and passwords, and then the server needs to confirm that the client is who they say they are, and then we can leave the world of passwords or something, but that's just not how this works. We have passwords, but we need the trust, right? It's not like the server has any mechanism of sending you a username and password or something like that. Doesn't even make sense in the web. We use public key cryptography. Yeah. Cool. So hopefully that all makes sense. Even with this data, you need a password. I mean, so we're just a server. So the client can now trust us enough to send us a username and password, right? The real objective here is that the client, before they send their username and password, wants to make sure they're talking to the right website. And that's what HTTPS gives us. It says, you are in fact really talking to pwn.college, right? The S. If we don't have S, we remove all of this cryptography. You don't really know that you're talking to the right pwn college. Someone could be man in the middling you, right? In this case, after doing all of this, we're talking over an encrypted channel, that the server has verified is good to go. Right, this is the part where, so before we are talking over some encrypted channel, right? When we derive this S, we're talking over some encrypted channels. Sure, it's encrypted, but it might just be encrypted with Mallory, right? So who cares? You could be talking encrypted to Mallory, this hacker. That's not that exciting. It doesn't really offer us a whole lot of trust. This confirms, no, really, you're talking over an encrypted channel, and that encrypted channel is with me. And now we're good to send a username and password because I know I'm not talking to Mallory. And as the server, I don't care who I'm talking to. As long as you provide me a username and password, for my purposes, that's good enough for me. But for your purposes, before you send your username and password, you probably would prefer that you know that you're not talking to Mallory. And I guess to confirm, right, it continues to go over this encrypted channel. So there's no worry that the client should have that I send the username and password, and then the server sends back this cookie. And if we think about it, right, that cookie is very important because the cookie is what continues to authenticate you. The client doesn't have to worry that somehow Mallory is seeing that cookie, right? It's this two-way communication channel that is like locked into these entities because these two entities are the only ones that know the key. And so there's no way to like break this halfway through the chatting. So somehow Mallory just jumps in halfway through the conversation and gets to see that cookie. No, it's like everything's talking over these two, over this encrypted channel, and these two entities have that key, and they've already locked in the key. There's no like we're never recommunicating the key or something. So it's all safe. Yeah, it's really cool, honestly. Once you think about this, like we're using a few mathematical constructs that just have these weird kind of cool properties that maybe 100 years no one really thought of as being important. And they're really not that difficult of mathematical properties. But somehow using this like mathematical property, we can build up this scheme of trust. It's very cool that math can lead to trust. Um, yeah, and it does take quite a bit to understand of wrapping your head around, because we're kind of like intertwining these properties together very carefully. Because if you weren't thinking about it too much, you might not have done this step as part of TLS. You might just not do it. And you would be like, well, it's fine. I like kind of gave away my user certificate and like, hey, here's my user certificate. But Mallory could send you the user certificate, right? Mallory could send the legit signed off user certificate of pwn.college, right? I could try to be talking, so client could try to talk to pwn.college and really end up talking to Mallory. And we'll make this bidirectional or whatever. And when we do this step where we're like, okay, well, let me send you let's communicate. We've got a secret here, and we got a secret here, right? So these two can talk to each other totally fine. Then it's like, well, the client is waiting for a root sign off of Home College's certificates. Well, this is all just public information, right? The Mallory can know the certificate. This is all just like public key stuff. Mallory just sends Pwn College's certificate. Like, who cares? Like, I can do that as Mallory, and then like, what? Now you're gonna trust me? It's like, no, I haven't built in enough trust. We need to confirm that this S thing that we're using as the key for our encrypted channel right now, that Pwn College also says that S is good. We need Pwn College to say S is good. And guess what? This like RSA signature stuff in this certificate, is a E/N RSA public key. Is a Pwn College /E/N RSA public key. And Pwn College can sign Pwn College /A/B, right? So Pwn College says, hey, this is what I'm going to sign off on. Equivalent-ish to if they just signed Pwn College /S. It's just weird to send the key over the channel. It just feels a little awkward because you can get away with doing this and it conveys the same information. This is public things. Like, you don't care if everyone in the world has A and B. Like, this is expected that Mallory has this. This is like, don't start sending that. I don't know what would go wrong. Probably this is fine. It just feels a little awkward, and do this because we can. So Pwn College can sign this, which is the equivalent of this. And now we know that this S is safe. And Mallory, critically, cannot sign Pwn College A/B because Mallory does not have the B, the private key, associated with the public key, right? And Mallory cannot craft a custom certificate because root will not sign it. Root is not willing to just sign anything in the world. We need, in reality, the way that like Let's Encrypt and stuff works is like a popular way of getting this signing stuff to occur, is you do this sort of like challenge here, like at an earlier point in time. But you could imagine like show up with your driver's license or something. So Mallory can't just suddenly get a certificate signed off by root. And if Mallory presents a certificate not signed by root, client does not care about that certificate. It is fake. So yeah, we're like mixing together all of these properties. And if you look at it like in the browser, let's see here. Can I do this in Safari? Is there a way to do this? How do I view that button? Show certificate. Okay. Here's a root certificate. And where does this certificate come from? This comes from like Mac OS. It's just baked into the operating system that Apple has declared that we trust this. Okay. Apple trusts it, and I trust Apple enough to give me functioning hardware operating system thing full of good trust. So I trust Apple. Apple puts this thing in here and says we can trust this. Other people verify that this is a trustable thing. Like, you could imagine that on the news you would say like Apple has been shipping a bad root certificate authority. This is a disaster. Like people could confirm that this is a good root certificate authority. Like whoever this group is, like I could call them and be like, hey, is this your, where is it? Is this your public key? Whatever this entity is, I could like go to them. If I don't trust the phone call, maybe I'm worried my phone call is being tapped or like tampered with or something. Get in my car and drive to ISRG and confirm with them that this is the correct public key. And if it's not, go to CNN or whatever and publish this big report about how this is all fake. And then they trust R3. And then R3 trusts pwn.college. So you'll see, for example, pwn.college's, where is it? So for example, the DNS name, it's actually got 3 DNS names associated with it. It's got dojo.pwn.college, it's got pwn.college, and it's got www.pwn.college, all as considered good to go. What else am I looking for? This is the thing that does that challenge response thing. That's basically like an HTTP challenge response thing and they can automatically confirm that we're in control of this server. This thing has been signed. It all says like what the schemes are. So in this case, we've talked about SHA-256. This is something we actually haven't talked about. ECDSA. I don't know. I feel like I've heard people say EXTA. I don't know if that's true. This has to do with elliptic curve cryptography. In the same way that we do this weird, funky, circular. Well, actually, this is more along the lines of the RSA thing. So the way that RSA works is like factoring 2 prime numbers is hard, or factoring a composite number of 2 prime numbers that are very large, whatever, blah, 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 blah. It's hard to factor numbers is what RSA relies on. Elliptic curve cryptography relies on a different property that has to do with elliptic curves. And this is kind of the more modern standard, and part of the reason for that is it's actually just smaller keys. So RSA, you need like this 2048-bit number or 4096-bit number, which you have to convey all of that. Well, it turns out elliptic curve, you can do it with smaller numbers and be just as secure. One of the reasons. You can embed like what's the purpose of this server authentication, client authentication. I guess there is also, maybe we're doing RSA and our signer had ECDSA, elliptic curve. Where is like the thing? Somewhere in here there has to be a public key. Where is that? There's also like it's not valid before March 1st, 2024, and it's not valid after May 30th, 2024. So we were saying it's only valid for this long. Do the challenge response again to automatically get it again. Key size. Public, here it is. Here's our public key for pwn.college. Honestly, if you're asking me whether I can confirm that this is true, I hope so. I don't know. I'm not the right person to talk to, even though technically it's like kind of my public key. I don't know if this is correct. We're just assuming the whole system is working as intended. And you'll see that the exponent part of the public key is 65537. Cool. Hopefully that is a fun little dive into this. There's all sorts of other things going into this. In our case, we built up this challenge, and our certificates are just this, right? A name, a signer, and a key. Technically, we have stuff like dates in here, before dates, after dates. We've got things saying what type of cryptography we're doing here, whether it's RSA or elliptic curve. We've got things saying like, oh, the purpose of this is for server authentication. Technically, someone is willing also for us to say that we could use this for client authentication. Technically, you can use this whole scheme to also do client authentication. This challenge does not have it doing client authentication, but there's no reason you couldn't have both share their certificates and both verify the certificates. And then both verify that the Diffie-Hellman portion is correct. Says that, hey, this is the DNS name associated with this key, so when the web browser cares about this thing, because you could imagine using this certificate for stuff other than DNS-related stuff. But this is kind of what ties the domain name to the public key, et cetera, et cetera. Okay, I feel like I've talked a lot. Let's see here. That challenge that root does can be spoofed in any way, or is that impossible? That challenge that root does, can that be? No. Well, okay, not exactly. So you're asking, I talked about this, right? That where is it? This, right? Where we say, root says, okay, if you control pwn.college, really, I think I'm adding an unnecessary step. It's really just if you control pwn.college. I don't think the IP address is associated in here at all. We're just assuming this has to do with a different trust layer in your, in DNS, that the DNS server is trusted, which is a different perspective on trust, a different part of trust, different element, I guess we'll say. It just says, okay, if you control pwn.college, and we're all assuming that the DNS for what pwn.college is the same thing, make it so when I curl, and root knows that their DNS is correct or whatever, right? The pwn.college, how that resolves to an IP address, they know that they've got their stuff set up correctly, that they're interoperating with the rest of the internet, and they know what pwn.college means. They know that that means that this IP address. Well, they better be able to hit this website. I get HTTP 200 content length. Really, just this is the critical part. Like I root, and there's a way that you do this. This is all in and of itself a cryptographic scheme to make sure that, you know, if you don't do this carefully, weird stuff can start happening, I guess is what I would say. So for example, if pwn.college is just willing to always do a challenge response to whatever someone asks for, then Mallory could go to root and say, hey, sign off on this public key here, please. This is pwn.college, sign off on here. And then root will say, okay, here's your challenge response. And then you could imagine that Mallory then takes that challenge response thing, talks to pwn.college and says, hey, confirm this, make this work. And then if pwn.college made that work, then like now Mallory has a signed off thing. So there's a careful construction of how to make this work such that pwn.college, for example, you might think, how do we solve this? As if pwn.college can see that root signed off on this secret, so that the thing for me to sign is this. Well, I guess even that's not enough because Mallory could take that and have root would have signed off on it. You have to be careful there. Well, let's see here. Let's encrypt protocol. How it works. This is the core idea. There's some things to make sure that Mallory can't just forward this along. I mean, really, I guess what we need to do is to assert that pwn.college is starting this thing. right? So pwn.college probably needs to talk to roots first, and that's the thing that we need to bake into this scheme. Pwn.college goes and talks to, we'll say, we'll keep calling them root, really, it's Let's Encrypt or whatever. And probably they want to control part of this. So one way that you get around the fact that Mallory could do some weird stuff like just forward the challenge response to us, we want really to assert that pwn.college has initiated this. And so what pwn.college could do, pwn.college says, here's a random thing, right, to root. And then root says, make this thing, comma, appear at HPS, at HPE pwn.college challenge, right, for example. I mean, you can think about how to do this carefully, but this is, for example, how you could solve Mallory doing it is that we want to initiate, the way they initiate is that pwn.college also offers something that's going to be built into there. And so if Mallory did this, Mallory would have to be putting their own thing in, and like pwn.college is going to say, why the heck would I ever make that appear there? I didn't control this first half. Like, do it very carefully. There's those sorts of considerations that go into it. But yeah, so if you do this wrong, I mean, it could be spoofed. But it's all constructed very carefully such that someone cannot spoof this. Yeah. Or at least hopefully. I'm getting a untrusted user certificate, invalid signature error. Untrusted certificates. Untrusted user certificate, invalid signature. Yeah, so this thing. Yeah. Okay. That means that something is going wrong in this. So it sounds like you offered up a valid user certificate because you got through these previous steps. The next thing you need to do is the crucial bit for this, of course, is going to be this part right here, the user certificate signature. You need to make sure that the user certificate signature that you send, right, this is the thing that you're sending and that's getting checked. User certificate signature, you'll see that user certificate signature, which is this, where is it? Yeah, this guy. User certificate signature appears in this portion of things. So it's related to user certificate check. User certificate signature is used to derive user certificate check. And so you'll see what's going to happen here is that we hash. So user certificate hash is the user certificate data. So before it's JSON loaded, but make sure, for example, you're not hashing the base 64. Don't hash the base 64. Hash the raw bytes. Okay. There's a lot of subtle nuance here. Make sure you're hashing the raw bytes. Basically, the thing right before it's JSONified or JSON loaded, right? Or I guess in your position, you would have done JSON.dumps on this certificate. That is a blob of bytes. You are going to hash that blob of bytes. Okay, you will have run JSON.dumps on that dictionary and then hashed it. And then what you will do is you will do int from bytes of this hash. So the hash will be int from bytes. So we're going to convert this sequence of bytes into an integer. We have to convert the bytes to an integer so that we can do RSA math on it. Okay, so take this thing. So you have a certificate, you JSON dump that thing, then you hash that thing, then you convert that thing to an integer by making it a little endian integer, int from bytes the result of this thing as a little endian integer. Then we're going to take the user signer key, which is the root key. We're going to raise it to the d power, right? And we know what d is because it's told to us right away that this is the value of d. So we'll raise it to the d. Mod n, convert that integer, because right, we're doing RSA math. This is done on integers. Convert it back to bytes. Convert it back to bytes. So 256 bytes is a little endian integer. So now we've got bytes again. And you will take that sequence of bytes, and then I think you will base 64 encode that thing. Make sure it's also the right length. Length user certificate hash. Yeah, make sure it's the right length. Well, maybe you don't do that there. I don't know. You'll mess around with it. Here's what I would encourage you to do. If you're ever confused about what's going on, there's nothing stopping you from taking all of this code and like putting it, like all of level 14 code plus all the imports or whatever, dump it into a file. And if you want more logging at any point, add more logging, right? So for example, instead of just printing untrusted user certificate invalid signature, make it also print what the heck is user certificate check and what the heck is user certificate hash, right? So obviously these things are going to be different. And then add more debugging statements, like print out what is the POW of the, like back reverse engineer it by adding more code. It's very easy to add print statements into this. Yeah. So I would encourage you to take the challenge code, add print statements into it to get whatever insight you need into the whole process. Cool. All right. Thank you all for attending my office hours. I think there's maybe another office hour starting soon. I don't know. I should probably end soon. Make sure that I don't conflict with someone else that might be starting. Good luck with the assignment. And goodbye. See you in the next office hours.